I want to multiply two vectors and get a vector. The process we are using only applies in 3 dimensions. So as much as I would like to say this one generalizes like the dot product does, it doesn't. There are other exterior products that do similar things to this, but the cross product only works in R3. So I'm going to have two component vectors, A and B. And when I do the cross product, I'm going to get another 3 vector. The following formula sucks. And I must tell you that I hate this formula. White hot passion of 1,000 suns. Because there's a better way to write this. But it requires us to know something from a different course. So let me sneak something in on you. I want to use a determinant. Now, a determinant is based off a recursive idea on arrays of numbers, matrices. Those of you that took a linear course, you've seen this. If you haven't taken a linear course, you'll be like, what the? I promise it's not that crazy. Given an array or a matrix of numbers, we'll start with 2 rows and 2 columns, a 2 by 2 array. The determinant of this array, I'll replace those brackets by straight lines, is AD minus BC. You multiply these 2 numbers together, you multiply these 2 numbers together. When you're going from left to right, down, you add. When you're going from left to right, up, you subtract. So the AD, and I subtract BC. Because one of these is going down, one of these is going up. Make sense? Those of you that haven't seen it, maybe. Maybe. An example. The matrix 1, 3, 5, -2. Notice I read across the rows 1 top and then the bottom. So what I do is I multiply 1 times -2. I multiply 3 times 5. This is positive because we go down as we go from left to right. This is negative because we go up as we go from left to right. So I get -2 minus 15 or -17. Better? Jack, Yana, better? Best part. This is recursive. I don't want 2 arrays, I want 3s. So let's figure out how to do this. For 3. There are multiple ways to do this process. The recursive idea breaks this into 3 2x2s. This is called a cofactor and minor expansion. Now, what normally I would tell you is you pick any row, any column. But I'm going to make a specific choice. I say we're going to go across the top row. What we're going to do is we're going to take each thing in the top row one at a time. And we're going to cross out everything else in that row and that column. So I take the A, and if I cross out the B, C, the D, and the G, I'm left with these four: E, F, H, I. Now, every time I move across my row, I change signs. So A was positive. When I step over to B, B is negative. But now I cross out the rest of the first row and the rest of the middle column, and I'm left with D and F in the second row, G and I in the third row. And then I move over again, move over to C. I move over, I change signs. And I cross out everything in the top row and everything in the third column, and I'm left with D, E, G, H. But I know how to do 2 by 2s, right? Yay! So now I know what to do from here. And I end up with a number, and a number. Right? Now, I could keep going. If I had a 4-row, 4-column array, I could break it into 4 3-by-3s, and then I could break each of those into 2 by 2s. This process iterates. You make as big as you want. It's not easy once you get beyond a certain size, but this one works. Does this have to do with vectors? In order to do this, I look at this a little bit more closely and I say, wait a minute. A2, B3, A3, B2. What's missing from this first piece is anything that had a subscript 1. Here, A3, B1, A1, B3, there are no subscript 2s. And here, A1, B2, A2, B1, there are no subscript 3s. It's almost like I chopped out that section, like I chopped out the first or the second or the third section. Aha. So here's what we're going to do. I'm going to write a determinant for my cross product. I'm going to put A and B in the second and third rows. And in the top row, I'm going to write my unit vectors, I, J, and K. Now what I'd like you to do is do that cofactor and minors expansion on this thing. You get this, right? But now I'm going to do the 2 by 2s. So when I do the 2 by 2s, I get I times A2B3 minus A3B2. Then I get a minus sign, minus J. A1B3 minus A3B1 plus, do the K part, A1B2 minus A2B1. With me so far? This is written in IJK form. What happens if I put it into components? I did skip the middle one on purpose because there's a minus sign outside that J, right? So if I want to rewrite this in components, I need to distribute that minus sign. That'll make this the positive thing, A3B1 minus A1B3. At which point I have this wonderful eureka moment, and I say to myself, that is exactly the same as this. So if I can remember how to do this determinant process, I don't have to memorize the stupid formula. And I hate memorizing formula. So I almost always, when I am doing a cross product, I write out this determinant. And I do it exactly this way. So let's do an example. Now I cheated. And I pulled off the formula at the top, so we can't see it. I want to do this from the formulation using the determinant. So these are the second and third rows. But on top, go Ij and K. And as I start doing my cofactor expansion, as I write this down, I write down the I, and in my head, I do this. When I do that, there's the remaining submatrix. When I do J, I do this. There's the remaining submatrix. When I do K, I do this, and there's the remaining submatrix. So in my head, I've got two fingers, and I'm crossing out the appropriate column to give me the little 2 by 2. Then, what do I get when I do the 2 by 2 here? Remember, when we go from left to right multiplying, if we're going down, we add. If we're going up, we subtract. AD minus BC. So here, negative times negative is positive. Positive times positive, positive, I get 1 minus 4. Negative 3 minus 4, 6 minus negative 2. Now here's your choice. Do you want to leave this in IJK? Because then we can write minus 3i plus 7j plus 8k, or we could put it right back in components. Ta-da! Frequently, these two steps get mushed into one, Because my brain goes, oh, 1 minus 4, just write down the -3. -3 minus 4, just write down the 7. Oh, wait, I got to switch the sign. So sometimes and you already saw me make a sign error here. Sign errors are going to kick my ass all over the place here. Be careful. I said this only works for vectors in 3 dimensions. I hope you see why it only works. I need all of the numbers to make that little determinant. But if I had vectors in 2 dimensions, I could kind of sneak these vectors from 2 dimensions to 3 dimensions. I could say, hey, wait a minute, 3, -1 is in the xy plane. If it's in the xy plane, what's its z value? Same thing with 2, 2, right? So I could kind of make these into 3-dimensional vectors. So I can think of 2 dimensions as kind of being shoved into 3. I just can't make anything bigger because I'll lose information to come to 3D. Make sense? I'd like you to do U cross V. I'd also like you to do V cross U, but let's do this one first. You copy. If you finish UV before I get back, do VU. I'm going to go for my one. Be right back. So as I start to do this, when I do U cross V, the first thing I notice is that in the I matrix, there's a 0 in the first row and the second row here. So I'm going to get 0 minus 0. This is going to be a 0. Same thing here. 3 times 0, 2 times 0. But now when I do the K, I get, so there's my 8, right? 6 minus -2. U and V are in the XY plane, right? Three, -1. No. Yeah, X is positive. Y is negative. That points this way. 2, 2. X is positive. Y is positive. Points this way. Yet their cross product goes straight up. What happened when you did V cross U? Hey, wait a minute. Same reasoning. 0I plus 0J. Oh, -2 -6, it's -8K. Holy crap. Wait a minute. Wait a minute. Something weird just happened. This is, for most of us, the first time where we get to see something where order matters in multiplying. A times B is not the same as B times A. Here's proof. The order in which I do these matters. But again, 3, 1 in the XY plane, 2, 2 in the XY plane, and my cross product is straight down. Two important things come out of this. The first is that cross products are perpendicular to the products, to the vectors they come from. This is actually on page 816 as a theorem. So let me ask a seemingly stupid question. If it's a theorem, I should be able to prove it. It's what we did in discrete math. It's what we do in all of our logic courses. It's what we do in math. Damn it, we prove things are going to be true. How do I know whether or not two vectors are perpendicular? Which is it? The dot product is, we did this on Friday, 0. So I would have to calculate A cross B dot A and A cross B dot B. But notice, if this is the vector V, 2, 2, 0, and this is the cross product, 0, 0, 8, 2 times 0, 2 times 0, 8 times 0, I get 0. 3 times 0, -1 times 0, 8 times 0, I get 0. This is true all the time. And on page 816, they actually compute out in general what happens when you do this cross and dot product together. A cross B dot A. And we get 0 every time. But the other thing that happens is that the order in which we do the multiplication matters. And it turns out that U cross V is negative V cross U. Whenever I change the order in a cross product, I get a different sign. Now, Let's go back to the two we were using. 3, -1, 0, 2, 2, 0. I want you to use your fingers. Point your first finger in the direction of 3, 1, 0. Sorry, 3, -1, 0. This vector, 3, -1, 0. Points forward, because the x is positive, and slightly left. Sorry, slightly right, if you're pointing out in front of you. Yes? Because it's negative. Now use your second finger, 2, 2. Points forward and left, yes? Now stick up your thumb. Perpendicular to both of those, the cross product goes up. 0, 0, 8 went up. But if I do the multiplication in the other order, I have to put my first finger over here, my second finger over there. That doesn't work right. I want to use my right hand rule. So instead of doing this, I turn my hand over, U, V, cross product goes down. Just like our axes, I have a right hand rule for the direction of the cross product. Now, again, in some textbooks, you won't see them use their fingers. You'll see them point the entire set of fingers in the direction of the first vector and curl their hand in the direction of the second vector. So the second vector is coming out of your palm. So A, B, cross product. You'll see this if you're taking physics 2 this semester, when we get to electricity and magnetic fields. All of those are vectors. Sneaky mother. I love it. Now, I want you to understand, I had a very difficult time teaching this idea last semester. I don't know how many, any of you know Ruby DePalma? Her right arm ends at the elbow. So I kept going, I'm sorry, but it's all right-handed. There's nothing I can do. Ryan Ressler, child of one of the admins over in the PA, also only had a left hand. And so we kept trying to do the turned version of this the entire semester. It worked. He was okay with it. He was okay with it. But this is right-handed. Why? Because so many human beings are dominantly right-handed rather. I apologize to all the lefties in the world like my wife, but we're stuck with it. Questions? I'm back to geometry. Because I can draw a picture about the way this works. And it turns out that if I have any two vectors, let me draw our two vectors that we were just using. Three, -1, 2, 2. Right? There's U and V. Just like I did with the dot product, I'm going to let this be the angle theta, the angle between them. The cross product vector, U cross V, goes that way, comes up, out at us, right? U, V, my thumb will be coming out of the page towards you. I would like you to draw the parallelogram you get if we were going to go do U plus V. Right, you'd make a copy of V at the end of U, you'd make a copy of U at the end of V. So if I did that, I'd get those two dashed vectors, right? I'm a crappy artist, so I'm okay with that not looking real good. But that's a parallelogram, yes? Anybody know the formula for the area of a parallelogram? The internet is your friend. Look up the formula for the area of a parallelogram. Just like a rectangle, right? Base times height. Problem. Where's the height? Uh-oh. Where's the height of this parallelogram? Well, I've got to go from one side to the other. So I need to draw a perpendicular line. There. That's the height. Wait a minute. I've got a little baby right triangle right here. And I go back to my trig like I did on Friday. I say, oh, the height of that is the length of the hypotenuse times the sine of the angle, because the sine would be h over the length of v. So the height here is given by this vector times the sine of this angle. H equals length of v times sine of theta. What's the base in that particular thing, given the way I've drawn h? That would only give me this part. I want the whole thing, right? That would be the length of this other vector, wouldn't it? Hey, wait a minute. The area of this parallelogram is the length of u times the length of v times the sine of the angle between them. So the cosine part gave me one thing. The sine actually gives me a physical area. Now we can prove this using geometry like I did. We can prove this algebraically as they do in the text on page 817, but I think the algebraic version is much less, quote, obvious than this. I've seen this picture a bunch. But that means this is the length of my cross product. So it turns out that in our example, we end up with exactly 8 square units in this parallelogram. The dot product was AB cosine theta. Cross product is AB sine theta. By the way, if you know two sides of a triangle, you can find the area by finding the third side and then using Heron's law for the area of a triangle, but that's a real pain in the ass. What happens if you cut that parallelogram in half? You get a triangle where you know two of the sides. So the area of the triangle is always half the area of the parallelogram, which I can get from the cross product. If I only know two sides, that's good enough. You know who does this a lot? Surveyors and civic engineers. I stand at one point, I put a reflector at the corner of the property, another reflector at the other corner of the property, I measure the triangle of area. Just by knowing this distance, and the angle between them. I want the area of an irregular, straight-sided field. That's how I get it, by cutting it up into little triangles. By the way, that original idea goes back almost 3,500 years. We have evidence that that was used to calculate area of land in Egypt. Not in vector terms, but using the geometry of triangles, because when the Nile would flood, it would wipe out all the landmarks. And they'd have to go back and restake all of the fields out. When you restake the fields, they measure the fields so they know how much to tax you. Questions? There's a problem that asks you about a right triangle. It was in the last section, right, that you were asking me about? And you had to use the angles carefully. An important note is that you have to make sure that the vectors you are using have a point in common at the vertex, so that you're using the correct pieces in your triangle, as opposed to doing them in two different directions and getting the angle on the outside of your triangle. There's a bunch of algebra that goes with cross products, but I would point out to you a question. When is sine of theta equal to 0? Oh, I used A and B, and then I used U and V. Let's not do that. This should be U, this should be V. Got to use the same vectors in both damn parts. Great question. And vectors whose angles between them are 0 are parallel, and vectors where the angles between them are pi are antiparallel. So U and V are parallel if and only if U cross V equals 0. Now notice something different. When I wrote the dot product, I wrote A dot B equals 0, the number. When I do the cross product, I get out a vector. So I write out A cross B equals 0 as a vector. The most common vectors we will take the cross products of, I cross J is K. J cross I is negative K. There's my antisymmetry. I cross K. No, I can't do that. I cross K. There we go. Minus J. K cross I is J, just by moving my hand. A lot of the algebra rules we like work. Unfortunately, commutative property was the one that we lost. Page 819, anti-commutative behavior. But I can distribute numbers. I can distribute cross products across addition. I can distribute it on either side. This one. This is interesting. If you have multiplication, shouldn't the order in which you multiply not matter? Ooh. A dot B cross C is A cross B dot C. What the? Oh, and by the way, this triple cross product, I've never used. So the formula's here, but literally I've never used it. I want to look at that fifth one a little bit more. A dot B cross C. Let me write that down. Well, my first question is, why are there parentheses around this? Think about this for a minute. If I write it without the parentheses, you don't know which one to do first, do you? Except if you do A dot B first, what do you get? Can you multiply a scalar with a vector using the cross product? No, you can only cross a vector with a vector. So I can't do A dot B first. I have to do B cross C first. The parentheses are really kind of not necessary. But if I wanted to try and rearrange which one was crossed and which one was dotted, then it would matter. And that's what Rule 5 tells me. But again, I've never actually used that in a calculation. I've never seen it used in a proof. So in spite of the fact that it's an interesting rule, this one's like, it doesn't do for me. There's a joke in here. What do you get when you cross an elephant with a grape? Elephant grape sine theta. What do you get when you cross a mosquito with a mountain climber? You can't do that. You can't cross a scalar with a vector. Mosquitoes transmit diseases. They're disease vectors. Somebody climbs a mountain, they're scaling the mountain. Told you there's a joke in there. I didn't say it was good. This, on the other hand, this is meaningful. This particular calculation is actually useful. I'm going to draw 3 vectors. And I know because I suck at drawing, they're going to look like they're all in the plane. But we're going to have 2 of them flat. And the third one, I want it to go up at an angle. So none of these are at 90 degrees to each other, right? So don't make the right hand roll with your fingers, kind of squish them in a little. I want you to imagine that we draw all sorts of parallelograms. I could draw a parallelogram for A and B. I could draw a parallelogram for A and C. I could draw a parallelogram for B and C, right? And I'd get this funny looking corner. It wouldn't be made of squares anymore. It'd be like it kind of got the rectangle, the box got tired and kind of drooped over. What we get is called a parallel pipette. Parallelepiped. Parallelepiped. And it looks, again, like a squished box. Bottom of page 819, a parallelepiped. Please don't fall any further. Thank you. Okay. Now they've even labeled them in a different order than I did, but I don't care. Let's think about the bottom base parallelogram here. In this picture, that's the one made out of B and C. What's the area of that parallelogram? But I have the cross product to do that work for me, right? The area of the parallelogram is the length of A cross B. But this is a solid box. And a 3-dimensional object's volume is base area times height. So I would need the height from the bottom BC parallelogram to the top parallelogram, right? The cross product sticks straight up from both of those. And that's this vector way over here on the edge, B cross C, sticking straight up from B and C. What I need to do is I need to take A and figure out how much of A goes in that direction. We did that Friday. How do we figure out how much it goes in one direction? We use a projection. What's our formula for projections? Okay, but it's times using the dot product, right? But the dot product can be gotten by using the cosine of the angle, can't it? And if we look at this picture right here, this angle, theta, is exactly the projection angle I want to use. So instead of me using that formula for it, Mia, instead of using that version, I'm going to use the cosine version, but that means I'm going to use a dot product. A dot B cross C tells me exactly the projection over here. And that tells me how long this piece is. The cross product tells me the area. This thing is volume. And it's the volume of this cell. Holy crap. This number, whatever it turns out to be, because I'm going to take a dot product, I'm going to get a number. This result is the volume of this parallelepiped. Now, I really need to be careful because it is possible that one of these cross products might be, or one of the dot products might be negative. I should take an absolute value. Although, if you think about right-handed versus left-handed chemistry, we talk about chirality and handedness. If we ended up with a negative number, what that means is that something is backwards from the way we like to label them. It's left-handed rather than right-handed. That's okay. We can have a negative in our answer. We're going to use the absolute value much more often. Because of this, returning a number, this is called a scalar triple product. In addition, I don't have to do it as separate steps. I don't have to do the cross product first and then do the dot product. I can do it all in one single calculation. A dot B cross C. Well, normally I would have B1, B2, B3, C1, C2, C3, and I'd have I, J, and K up there, right? But when I do the dot product, I take the first part of A and multiply it by the first part of the cross product. That would just get rid of the I and replace it with A1. So let's do that. Same thing for A2. Same thing for A3. So I can actually do the scalar triple product in one step. And it's one determinant. We will see this again when we start to do integrals in this course. The end of chapter 15. We'll use exactly this idea again for the volume of a piece. Crystal structures. I think this one's called orthoclinic, but I'm not 100% sure. It's been a long time since I did chemistry and crystals. But crystal structures have cells exactly like this. And when you've got parallel planes, you get cleavage planes, you get vibrationary planes. Quartz crystals are in this sort of shape, and that's the reason they work as resonating crystals for electronic devices. The way your clock on your phone, the clock in your watch works. A quartz crystal vibrates when you push electricity through it along the planes made by these bonds. My other favorite cross product is torque. Somebody tell me whether you know whether you're screwing something in or out. Why? Ready? Take your right hand. You're applying a twist in the right direction. Yes? Which way is the cross product going? In. You're applying a twist in the left direction. Torque is a cross product. When you screw a screw, you're using this idea. The distance and the force you apply, A cross V. We use R for radius and F for force. You apply a force at a distance with a wrench. Every single AAA car rescue person has in their pile of stuff a 6-foot length of hollow pipe. You know why? Because the lug wrench on your car is only about that big to take the nuts off your tire if you have to change a flat. Not going to get a lot of torque out of that, are you? Put a longer handle on it, you get a bigger torque. Length of R times length of F, bigger handle, more torque. Useless. I saved my changing flat tires because I knew this. I got a piece of pipe, made the handle on it. Pop, that sucker came right. Wednesday is question and answer. Homework is due Thursday. I will see you all then. Have a wonderful rest of your day, everybody.